We're now going to look at a pretty significant process that involves arc length and the idea now of, again, we have the nonlinear motion that's defined by a vector function. So let me start with a little picture to kind of give you an idea of what we're trying to accomplish here. So let's say we have this point. So I'm not going to draw all the position vectors that like we've done in the past, but this point here is the terminal point of the position vector r of t0, right? So let's say, and this is going to be referred to our reference point. So this is our reference point. So in other words, our motion starts here, right? And then we are going to travel along the curve for a certain amount of time, and then we're going to get to another point here, right? Now, one of the main reasons why we use t as our parameter is that we can interpret r of t and I mean we've done this. In fact, this is how we came up with the idea of computing things like velocity, acceleration, etc. We interpreted this as the position, right, of, let's say, the object at time t. Right? So if we travel for a certain amount of time, right? So let's say this is t0 here happens to be t equals 0. Suppose we start analyzing motion at t equals 0, and then we travel for 5 minutes. Then if I plug 5 into this function, it will tell me where I am after traveling for 5 minutes. But suppose we wanted our position to be a function of not time, but instead our distance traveled. So let's flip the question and say, what if I were to travel for 5 miles along this curve? Where would I be at the end of my journey, right? Which is different from asking the question, if I travel for 5 hours, where will I be at the end of my journey? So essentially our goal, so let me just write what we would like here. We would like to express position not as a function of time, but instead as a function of distance traveled, right? And that's why we're going to use, so we're going to use our little s for distance traveled, right? So essentially, we will know the position as a function of time, and we want to change the parameter from t to s. And no, we can't just erase all the t's and put an s there. No, in other words, it has to be consistent with everything that we've previously defined in terms of arc length. Well, so let's take a look at what we know about arc length. So we have this formula previously where the arc length, or the distance traveled, is our integral from t0 to t1. What do we integrate? The magnitude of the velocity, right? Pretty straightforward. But the thing is, what we're saying now is we are going to, we'll still have this fixed initial time, but the time that it's going to take me to travel the distance that I'm interested in is now going to be a variable. So what I need to define now is not just a distance integral, which is what this is, but instead a distance function, right? And before we get into the details of this, I just want to remind you that that concept again goes back to the fundamental theorem of calculus and area functions. Let me just do, so this is going to be we're going to do a little flashback here. So we're going to go back, because again, this is such an important concept. I feel like whenever I get the opportunity, I have to hammer home that idea. So remember what we did to define area functions, right? And again, I'm not going to get into all the super specifics. That was done before, but basically what we said was we had a fixed lower limit, and then we had a graph where our function was in terms of t, right? And this was our t-axis. And then our upper limit was allowed to be a variable x. And we defined our area function to give me this area. So our area, right, which depends on my upper limit, I mean, we know what that is. It's the definite integral from a to x. And then we would integrate the function f of t dt. And again, the thing to remember is the variable t here is what defines the curve. The variable x here is what defines what defines the width or the length of our interval. It's the upper limit of integration. And that's why we can't have x and x and x there, because they're essentially two quantities here that are changing, right? And somewhat independent of each other. Not entirely, because obviously the area is dependent on the type of function that we have here. But this is our area function, right? And what we're going to do is to do something similar, just to kind of revamp our distance formula and see if we can come up with a distance function, right? So this is our area function, and we're going to try to replicate this process now, but for the quantities, again, distance and time, and of course this is our speed. So think about it. Our distance is what we're going to use as our variable, but it will obviously depend on the time, right? But the time is unknown, right? So just like how, my area depended on x, and x was my variable, same thing here. T is going to be my variable. So we're going to put an upper limit there, right? But for the same reason, once I have this variable as my upper limit, I can't have my velocity be a function of the same variable. So just like how I have to make sure that these two variables are different, I have to make sure that the variable that I use here will be different from t. Now, I don't want to use something like x, because we're using x to represent a coordinate in either 2 space or 3 space. So obviously I can't use s. S is already being used. I can't use t. So I'm going to use something like u, right? So I'm going to switch this and express my velocity in terms of u, and then I can change this to a du, right? So this way there is no conflict with the variables that are being used, right? So this is what we're now going to consider our distance function, right? So our distance is a function of time, right? And again, of course, our velocity will play a role here. Yeah. So this this is what we're going to define as our distance function. Now, why is this important? Because, in fact, for instance, so if I now, I put the of t there just to really emphasize that, yes, this is a function of t. But basically, I have my distance variable here and my time variable there. So this equation actually gives me a relationship between s and t, right? So this distance function gives the relationship between my time variable, so between time and distance. So, and granted, yes, there's an integral that's involved, but technically, I should be able to express one in terms of the other. So right now, right? So let me restate it without the of t. So here is this equation. So right now, this expresses s as a function of t. Everything else here can be, again, in theory, be evaluated, but this expresses s in terms of t. But maybe what I could do is solve this equation and get t as a function of s. So in other words, it will allow me to replace t in my r of t with a function now in terms of s. So this equation right, I'll say if solvable for t gives us a way to, and the verb, so going from an r of t to an r of s, that process is called reparameterization, right? So gives us a way to reparameterize r in terms of s. Right now, there's a fancy theorem that goes along with it, but the theorem basically the theorem basically just states what the equation is, right? Which we've got based on two facts, right? What we know about area functions, we now use this concept of a distance function, and then obviously we have a formula for the distance expressed as a definite integral of speed. So we use those two facts, we come up with this, and let's see how it works, right? So let's do an example of this. So I'm gonna say determine the distance function. So the distance, sometimes it might say arc length, right? But we know that these two for us are equivalent. So determine the distance or arc length function of, and then here is our r. So r of t is equal to 2t 3 sine of 2t and 3 cosine of 2t, right? So right now, the way we're interpreting this, we have our position as a function of time, and we want to then express position as a function of s. And again, I'll say it, as much as we would love to be able to let's just erase all the t's and just put an s there. No, we can't do that, right? We have to be consistent with our distance formula. So let's carefully set up the integrand, right? So first we can find our velocity, and that we know how to do. So this is the derivative of 2t is 2. The derivative of 3 sine of 2t is 6 cosine of 2t. The derivative of 3 cosine of 2t is negative 6 sine of 2t, right? And if you wanted to right now, in fact, we could have done it up here. We could have just switched to that dummy variable u right away, but I'll just express, here is v in terms of our placeholder or dummy variable u. it is 2 comma 6 cosine of 2u comma negative 6 sine of 2u, right? Then we need to find its magnitude. So the magnitude of v of u, that would be, oh, not an angled bracket, a square root is what we need. So let me write down what's under the square root first. So this will be 4 plus 36 cosine squared of 2u plus 36 sine squared of 2u, right? And then we take the square root of that, and we see the same pattern that we've seen several times now with the Pythagorean identity, cosine squared, sine squared. So I get under the square root, out of the second and third terms, factor out a 36. That leaves cosine squared of 2u plus sine squared of 2u. And then again, what's in the bigger pair of parentheses, that is equal to 1. So under the square root, so look what happens. So this is basically saying that this trajectory, right, has a constant speed, because that's what we're computing here, right? So in fact, it turned out that just by, the process of computing the magnitude and using our trig identity, we would have gotten a constant anyway, because if you notice, the u goes away. But it doesn't always work out like that, right? So in this case, we have the square root of 40. And what would that be? So, well, let me just leave it as the square root of 40 for now. Right, we can simplify it in a bit. So now let's write down this arc length function. So s of t is the integral from, now I didn't give a starting value for t. Usually in a problem like this, if it's not stated, we can assume that the initial value of t is 0. So we can go from 0, but then our upper limit now is the variable t, and then we will integrate our speed function with respect to u. So this will be root 40 du. But again, this is just a constant, so it works out really nicely. So this just ends up being root 40 times u, right? That's my variable of integration here. And we're going to evaluate it at 0 and at t. So we end up getting root 40 times t minus 0. Now, root 40, that reduces to 2 root 10, and then times t. So this is my arc length function, right? So therefore, I'll just write it. So s is equal to 2 root 10 t. And this kind of makes sense, because if you think about it, what do we know about motion? Whenever the speed is constant, the distance traveled is simply your speed times time, right? So really, again, all those things that we know about motion, we're not breaking anything, we're just adding to it. We're looking at it more deeply, and we can do more, but all those basic principles still hold. So I'll just make a note here so that let's say, since the speed is constant, I'll just say we have the familiar relationship or formula that distance, I'll write it out in words, is equal to your speed times time. But again, this is only true whenever you have constant speed. Okay, so now that we have this relationship, right, let's now express our position as a function of distance as opposed to time. How do we do that? Well, if we solve for t, right, then we get this. Again, because the relationship is so simple, we get that t is equal to s over 2 root 10, right? So we solve for t, we may now express r as a function of distance traveled. Right? It doesn't always have to be function in, like r as a function of t. Now we're learning how we can express it as a function of distance traveled. So how do we do this? So I'll use r. I'll put a little 1 just to say that this is it's related to the original one, but it will involve a different set of formulas. So how do we do that? Well, r of s, just go back to our original vector function, and wherever we have a t, just replace t with the expression s over 2 root 10. So the first component was 2t. Now I'm going to write 2 times s over 2 root 10. The second component was 3 sine of 2t. Now I'm going to write 3 sine 2 of s over 2 root 10. And then finally, the third component was 3 cosine of 2t. And now I'm going to replace, again, the t with s over 2 root 10. Right? So here now is we have re-parameterized our position function, where now we know our position as a function of distance. So let's simplify. Basically, how everything simplifies is that these twos all go away, right? And we end up with this. So it's s over the square root of 10, comma 3 sine s over root 10, and then 3 cosine s over root 10. If you wanted to rationalize these, you certainly could. All right. Now, how would we use something like this? What kind of question could we use this to answer? So here's our final question. So where on the curve R, right, are we after traveling for a distance of pi root 10 over 3 units, right? So if we were, again, this is the same curve, right? Interesting thing is if we plot it in terms of s, or if we plot it in terms of t, it will look exactly the same. It is just defined differently. So it's the same object, but defined in terms of a different variable. So if we now know that we've traveled s units, s equals pi root 10 over 3 units, if I now want to, when it says where are we, so it's asking for the position, so all I have to do is take my new re-parameterized vector function and evaluate it at pi root 10 over 3. So wherever I have an s, right, replace it with this number. So it's really, you're just evaluating the function at this point, but now you're evaluating it based on or at a value that represents the distance traveled. So we have pi root 10 over 3 over root 10, right? So let me just kind of circle. So all of these, right, will be replaced with this, right? And then when we simplify, we will figure out where we are in space. What is our position? So 3 sine, and again, pi root 10 over 3 over root 10. And then 3 cosine of pi root 10 over 3 over root 10. So the root 10s, they all go away. So this one boils down to pi over 3. Here we have 3 sine. Again, the root 10 goes away, so pi over 3. And then finally, again, cosine pi over 3. So once we evaluate our sine and cosine, we have our values. Now, the sine of pi over 3, that's root 3 over 2. So we have pi over 3. This is 3 times root 3 over 2. And the cosine of pi over 3 is 1/2. So 3 times 1/2. So here's our position. So, well, this is the position vector, right? This is our position vector. So the terminal point of this position vector is where we are on this curve after traveling this many units. So we are at the point pi over 3, 3 root 3 over 2, and 3 over 2. Right? So it's a really nice example of how we don't have to be stuck using a particular variable there as our independent variable, right? If we can come up with relationships between one independent variable and another independent variable, then yes, we can switch between the two. We can't just switch it willy-nilly, right? We have to follow, all the definitions, all the formulas. They have to be consistent. They have to work well. But once we can establish that relationship, we do have the ability to switch from one to the other. And in this application, we're learning how to switch from a time variable to a distance variable. All right. See you in the next video.